Imagine this, you are on a quest to find the perfect rapture of joy, but your path is filled with obstacles and challenges. What if I told you that the key to success lies in strategic thinking and clever planning? Today, we are diving into the intriguing world of Jack Goes to Rapture, where math meets adventure. Ready to unlock the secrets of of this captivating puzzle? All right, let's dive into the logic behind the solution step by step. We are tackling a graph problem that involves around finding the minimum cost for Jack to traverse from one node to another. But before we start coding, we need to have a solid understanding of the concepts involved. So the first thing of a graph is a series of nodes connected by edges. Each edge has a weight which represents the cost to travel from one node to another. In our case, the node represents different locations and the weight signifies the challenges or cost associated with moving between different locations. For now, the first thing we need to do is to set up our graph. We'll create a list of edges for each node. This is done using a data structure called an adjacency list. It's efficient. It allows us to store only the connections that actually exist rather than wasting space for non-existent ones. In our code, we start by determining the number of nodes and edges based on input that we give. Then we initialize our graph, creating a list for each node. This is crucial because it sets the stage for how we'll represent our connection. Next comes the part where we read in the edges. For each edge, we not only add the connections from the starting node to the ending node, but also the reverse. This is important because our graph is unidirected, means you can travel in both directions on any edge. This dual connection allows our algorithm to explore all possible paths. Now let's talk about the core of our problem, finding the minimum cost to reach the last node. For this, we'll employ a classic algorithm known as Dijkstra algorithm, which is perfect for our needs since it efficiently finds the shortest path in graphs with non-negative weights. To keep track of the minimum cost to reach each node, we initialize an array filled with a value representing infinity. This indicates that those nodes are initially unreachable. We set the cost to reach our starting node, which is node 1 to 0 because it costs nothing to start there. As we traverse the graph, we need a way to prioritize which node to explore next based on the lowest cost. This is where a priority queue comes into play. We use a sorted data structure to always expand the least costly node first. By doing this, we ensure that we explore the most promising paths and avoid unnecessary detours. Inside our main loop, we continuously check the node with the lowest cost. If we have already visited this node, we skip it as we are only interested in the best part to each node. If not, we mark it as visited and examine all its neighboring edges. For each neighboring edge, we calculate the new potential cost to reach that node. Here's the crucial point. The cost to move to a neighboring node isn't just the weight of the edge. It can be influenced by the current node's cost. So we use a formula that factors in these relationships, ensuring we correctly calculate the minimum cost to each node. If we find a better cost for a neighboring node than we previously recorded, we update our records and update this node to our priority queue. This way, we keep refining our understanding of the best part as we explore the graph. Finally, once we have processed all reachable nodes, we check if we have a valid part to our node, which is the last node in our graph. If we find that the minimum cost remains as infinity, it means there is no valid path. Otherwise, we output the minimum cost to reach the last node. And that's the strategy. By carefully structuring our graph using efficient data structures and applying Dijkstra algorithm, we can determine the best way for Jack to navigate through his adventure. Now, with this understanding laid, we are ready to see how to translate this into code. But remember, the logic is just as important as the syntax, and that's what will make you and our solution robust and effective. Alright folks, let's quickly recap what we have covered today. We tackled the challenge of helping Jack navigate through a series of weighted paths to reach his destination in Jack Goes to Rapture using C#. And we built a graph representation of the nodes and edges, implemented Dijkstra algorithm and utilized our priority queue to ensure Jack finds the minimum cost to reach his goal. Key implementation details included matching the graph structures within the list of edges, initializing minimum cost, and efficiently updating paths as we traverse the graph. The main takeaway here is the power of graph theory and how algorithms like Dijkstra can optimize pathfinding problems. We saw how leveraging a priority queue can significantly enhance performance by always exploring the least cost path first. And if you found this breakdown helpful, don't forget to like this video and subscribe for more coding challenges. And in our next video, we'll also dive deeper into graph algorithms, like exploring variations like A star and Belmont form. Make sure to check out the link in the description below. And so if you're eager to elevate your coding skills even further, stay tuned and happy coding.